on. Good afternoon, everybody. Welcome to sunny summer Monday of Chem 11:05 with your host, Dr. White. Yes, Julia, action. I got to get one of those things like they use in Hollywood. All right, couple things. First of all, I'd like to apologize to everybody. I forgot today's a holiday. Technically, I'm not supposed to have class, but I will. Why am I going to do that? One, I told people you should come. And two, I also, since I'm posting a video of this, don't feel you can watch it tomorrow, not today, for those who are not here. All right, let's get going. Got a lot to do. And remember, there's no such thing as a dumb question in my class, and I practice it in my world. All right, a couple important things. One, let's go to Blackboard. In the assignment area, you'll notice, and I sent out an email as opposed to an announcement, because announcements I can't attach files, emails I can. I made a mistake when I originally posted this. I forgot about it. That's two things I forgot about. I better have some fish, brain food. But anyways, I put the DL lab safety contract, not the COD DL lab safety contract. So please do this. I'm going to change this later today to Wednesday because today is a holiday. But if you've already uploaded it and it wasn't the COD, which is 2 pages, DL lab safety contract, please upload the right one again. You can upload more than one time the way I have these assignments set up. All right, that's number one. Number two, if you haven't submitted your signature sheet, please do that as soon as possible. And finally, while we're in here, don't forget, tomorrow the scientific method lab is due. And be sure to include a selfie now of you with a piece of equipment or a chemical for this lab, or you get 0 points. Why? Because that's departmental policy, which was set last semester, that for all home labs, each lab where we use chemicals and things like that, or parts, equipment from the lab, student has to include a selfie. Now, the selfie can be a separate file upload. And one of your colleagues asked earlier about that. You have a separate, like a graph or a selfie, that's okay. What I don't want is 6 or 7 JPEG files. Makes my life very hard, which I don't need ever. I guess you don't need your life being hard either. All right. Let me look at my list of things. And don't forget, hand in labs, they're easy points. Oops, I shouldn't have said that, but they're not hard points, but you get 0 points if you don't hand it in. All right, any questions on any of this? All right. Now, I promised last week that today I would go through chapter 1, problem set, so I will. Now, notice it says practice problems. Hint, after test 1, you'll know why I call them practice problems. Big hint. Everybody get the hint? All right, let's go through this. What is one of the 4 branches of chemistry? Well, the best is organic, but I'm biased. I'm an organic chemist. Analytical, physical, and organic. What is matter? Something that occupies space and has mass. Now, one you really should know, what are the 3 states of matter? and they are solid, liquid, gas. Now, I don't have a question here, but you should know a solid has definite shape, definite volume. A liquid has definite volume, but indefinite shape, and a gas has indefinite volume, indefinite shape. And since I try to make this class relevant to your daily life, I ask questions about that. Name a pure substance that you could use in your daily life. Well, water would be one, gold, oxygen gas, and O2, N2, nitrogen gas, and I could keep on going. Silver would be another example of mercury. What would be another one? Ammonia, but you don't work with that. I have. All right. Name a mixture that you could purchase at a local grocery store. Well, there are a lot of mixtures: milk, mouthwash, mustard, pop, and I guess you could put down another mixture would be salad dressing. Mayonnaise is a mixture. There are a lot of mixtures. All right. Oil vinaigrette dressing. Is oil vinaigrette dressing homogeneous or heterogeneous? Homogeneous, the same throughout. Heterogeneous, not the same. And if you remember, I showed you the picture of the wishbone oil vinaigrette. And there are 2 layers, and that means it's heterogeneous. Is gasoline homogeneous or heterogeneous? I hope the gasoline you're buying is like the one I am, and it's homogeneous. Because if it's heterogeneous, you're in big problem. None of you probably remember, but a colleague or a friend of President Johnson's was selling gasoline that he mixed with water. And water, by the way, is the cheapest chemical you can buy on this planet. And he was selling it and making a lot of money and ripping off a lot of people. All right, you should know the 37 chemical symbols from the periodic table and elements. Therefore, give the chemical symbol for the following: carbon, C; chlorine, Cl; silver, Ag; gold, Au; oxygen, O; sodium, N. A. Almost forgot the A. All right, and you should also be able to do the following: give the name of the element with the following symbol. And we'll just do a couple of these. My favorite, if you haven't guessed, so I'm an organic chemist, C, carbon. And I used a lot of argon in grad school, and I've never used and probably never will use krypton. Now, we talked about physical and chemical properties, and a physical property is something you can observe without changing that chemical, or doesn't describe how it could change. And water freezes at 0 degrees C. That's a physical property. Oxygen is a gas at room temperature. That's a physical property. I think I have the same one twice, and I do. Sorry about that. Iron can rust. That's a chemical property. Gasoline is flammable, chemical property. Give an example now, not a property, but a physical change, and that would be when something changes its physical state, but not its chemical state. Water boiling, ice melting. If you take sodium chloride, table salt, you can dissolve it into water. And give an example of a chemical change. Well, I like candles. I got a nice collection. I don't know if I told you this story. I got time for Dr. White's story. For a number of years, I worked for this company, Unichem Chemicals, which was a huge chemical company that was at that time part of Unilever. And Unichem was headquartered in the Dutch city, which you spell Gouda. Americans pronounce it Gouda, where the cheese comes from. Nope, it's Gouda. And I worked in Gouda, I would stay in The Hague, which Dutch really is Den Haag, and I'd take a train there. Well, one of the nice things in Gouda was a small little candle store with hand-dipped candles. And there are huge ones too, like that diameter. I've got a bunch. I don't think I'll ever burn them. They're so beautiful. But candles, when they burn, that's a chemical change. And when you digest food, eat food and it goes in your stomach and is digesting, that's a chemical change. And as we mentioned, iron rusting, that's a chemical change. All right. Any question on chapter 1? All right. Well, in that case, don't forget, you should try it on your own if you haven't. This Wednesday, I will do chapter on Appendix A2, A4 problem set. This Wednesday, I will do Appendix A2, A4 problem set. Why? Because test number 1 is coming up soon. All right. Now, last week, I started talking, really, I ended up sort of quickly, the periodic table. And the periodic table is based on the periodic law, which I'll never ask on a test, what's the periodic law? And I'll never ask, what's the periodic table? But you should know how to use that. Now, I think I have it in Blackboard, but I'll check after class. And if not, I'll post it. All right, where did I lose? Oh, I know why. Keep on forgetting. You can open. Here's the periodic table you will be using for this semester. Now, the periodic table is a list of elements, and you should know H is hydrogen, Li lithium, C is carbon over here, go next door, and nitrogen, oxygen. Now, this is a periodic table. Now, elements in the same column have similar physical properties, are part of the family name for that column. The only exception is hydrogen. Hydrogen, even though it's in the first column, is not part of the family of lithium, sodium, potassium, and so on. But you should know the first column, excluding hydrogen, is the alkali metals. The first column is the alkali metals. The second column, and the only two you have to know for my class, are magnesium, Mg, Ca, calcium, are the alkaline earth metals. The second column are the alkaline earth columns. If we go all the way over to the right, column 7, fluorine, chlorine, bromine, and iodine, those are called the halogens. How many of you have ever heard of halogen lamps? Street lamps. Some of the places are now changing over to LEDs, but the halogen lamps, the bulb in there contains halogen gas, which is why they're called halogen lamps. I don't know which of the halogens they put in there. Hold on, let's try something. They use a tungsten halogen filament. So there is halogen in there. All right. I've now learned something new. That's the nice thing about science and chemistry. There's always stuff to learn. Now, the last column, column 8, all the way on the right, helium, neon, argon, krypton, xenon, and so on, those are the noble gases. They used to be called inert gases until the late 1990s, when some chemists found a way to make them react. And if they react, they can't be called inert gases, and the name was changed to noble gases. Once in a while, I still call them the old name, but I try not to. Now, again, first column, alkali metals. Second column, alkaline earth metals. Seventh column, halogens. Last column, 8, the noble gases. And if I ask, give an example of a halogen and its chemical symbol, you could put Cl, chlorine, Br, iodine, or any other halogens. If I ask, give an example of a alkali metal, and that would be Na sodium, La lithium, K potassium. Alkaline earth metal, magnesium, Mg would be an example, and that you should know. And with that, we're done with chapter 2. Let's check. Periodic table. Oh, wait, not almost done. Now, there's something called metals, and I think you're all familiar with that term. What is a metal? It's an element that has the characteristic properties of luster. What does luster mean? That means you can shine it up so it's nice and shiny, like my gold ring, I could shine up. That about needs a cleaning soon. And that's luster. Thermal conductivity, it conducts heat. If you go in your kitchen, you'll look at your pots and pans, they're made of metal, because that's the best thing to conduct heat when you put it on there. Now, metals also will conduct electricity. That's electrical conductivity. And if you think about it, all the wires in your house, your computer wires, any kind of wires, are metal, usually copper. Now, some of the old HP calculators for long ago, they actually had gold wires in them. That got to be too expensive. Now, you should know example of a metal. Aluminum, Al, is a metal. Copper, Cu, is a metal. Au, which is gold, is a metal. Lead, tin, zinc. And there are other metals too. Now, one thing I forgot to mention is malleability, and that means you can beat on it and it gets thinner and thinner. You can make it thinner. How many of you are familiar with aluminum foil you use in the kitchen? Hopefully you all are. Have you ever noticed one side is shiny and the other is dull? When they take a big piece of block of aluminum, they run it through different rollers to make it thinner and thinner. That's because it's malleable. But when they go to shine it up, it's so thin that the way they buff it and shine it would rip it. But when they put two pieces together and run it through the buffer, it doesn't rip. Well, two pieces together, the top of each side gets buffed up and shine, but not in the center. And that's why aluminum foil only has one shiny side. Now, switches totally off. There's something called nonmetals. They lack all the properties of a metal, and they're metalloids that are important in our daily life, but I won't ask on a test. They have some of the properties of metals and some of the properties of nonmetals. And probably the most important one is silicone. And silicone and other metalloids are used in the chips, computer chips, in our cell phone, computer, your TV, and a whole lot of other things. And now I'm done with chapter 2. Which means it's time for a new chapter. And finally, we're going to get into some real chemistry now. Finally, Dr. White's really happy. And what is that new chapter? Chapter 3, called the atom. And what is an atom? An atom is the smallest particle of an element that retains all the characteristics of that element. You can't get any smaller particle of an element that has, this is important, all the characteristics of that element. Now, who came up with this? Switches off for here. One of the great chemists, an English chemist, Dalton, came up with his atomic theory. And that wasn't that long ago, 1800. If you think about it, it's only a couple hundred years ago in the history of mankind. That's not that long ago. And he came up with the concept, every element is made up of tiny particles called atoms. And I'm not going to ask you what Dalton's atomic principle is, but I still like to go over it. Atoms of a given element are identical to one another, but different from other elements. And when he made this is stuff that nobody had considered. And atoms of two or more different compounds combined to, or different elements combined to form compounds. A particular compound is always made up, and this should be of, not PF, of the same kind of atoms and the same number of atoms. And a chemical reaction involves rearranging, separating, or combining atoms. Now, this is very important. Atoms are never created or destroyed during a chemical reaction. When you have a chemical reaction, all you're doing is changing partners or pulling things apart, but the atoms themselves are never created and never destroyed in a chemical reaction. All right, let's talk about the atom, and let's talk about the parts of the atom. Now, the important thing, subatomic particles. What does subatomic mean? How many of you know what a submarine is? It's a boat that goes under the water. And by the way, I'm not going to ruin your day and start singing the Beatles song, Yellow Submarine, even though I like that song, but I won't ruin your day. Dr. White is not a singer. At least not when I'm alone, it's okay, but now you don't want to hear me sing. All right, now, subatomic, sub means under, those atomic atoms, those are the very small particles that are the building blocks from which all atoms are made. So subatomic particles are the particles that make up an atom. Oh, you know what time it is? It's time for Dr. White to be subtle. See how subtle I can be? And know this. So what are the subatomic particles? The first one is the electrons. And the electrons are subatomic particles that possess a negative charge, negative electrical charge. And you should know one of the subatomic particles are the electrons. And the charge on an electron is a negative charge. The second subatomic particle are the protons. And protons are subatomic particles. Remember, these are the particles that make up all the elements of the periodic table. And I'll scare you when I'm done with this table about looking at something, but remember, a proton has a positive electrical charge. It's got a plus charge. And finally, neutrons. And neutrons are subatomic particles that have no charge at all. Now, if we were in class together, I'd say, class, all together with me. What are the 3 subatomic particles? And you'd say electrons, protons, neutrons. And I'd look at you and say, oh, that was pretty lame, because everybody would do it quietly. I'd say, come on, with feeling. What are the subatomic particles? Electrons, protons, neutrons. And then I'd feel better. Remember, electron has a negative charge, protons have a positive charge, and neutrons have no charge. Now, how many of you have ever seen a TV cartoon program called Jimmy Neutron? If they were asking me, I'd call them Jimmy Electrons, because the electrons are a lot more exciting than the neutrons, but nobody asked me. So it's Jimmy Neutron. First time I saw that, I was already a chemist, and I said, wow, I would have called them Jimmy Electrons, but nobody asked me. All right, so these are the subatomic particles that all elements are made out of, all elements. Now, take a look and touch the back of your skin. Go ahead, hopefully it won't hurt. Go ahead. You feel your skin. That's made up of atoms, mainly carbon atoms and other atoms. And each one of those carbon atoms in your skin, you've got atoms that are made up of electrons, protons, and neutrons. But you never thought about it. Your skin is chemistry. My hair, what's left of it, don't look. Anyways, and my beard, those are made up of chemicals or molecules. I'll teach you what a molecule is later this chapter, next chapter. And those are made up of atoms. And the hair here, atoms are made up of electrons, protons, neutrons. So next time you see something like my wall, this cabinet, the metal there, the wires, anything that's made up of atoms, and those atoms are made up of electrons, protons, and neutrons. That's why I always laugh when I hear someone say, I hate chemistry, because what they really mean is I hate whoever taught chemistry. Hopefully you won't say that about my class. Hopefully. All right, now, when we look at an atom, which is made up of electrons, protons, and neutrons, how is it put together? Well, it turns out back about 1900, 1905, a number of chemists were doing experiments to answer that question. And one of the important ones I'll be subtle again. Can't know this is Rutherford's gold foil experiments. All right. You look on your screen, you'll see right in the middle where it's a gray in the middle, or over here on the right, let me move this. You'll see CK12 foundation. Underneath, you'll see gold foil, detecting screen, and alpha particle emitter. Now, what Rutherford's gold foil experiment was, he shot these very heavy, high energy particles at a piece of very thin gold foil. And what happened? Well, most of them went through, but some of them were scattered. In fact, if you notice, some of them came straight back. Think of this experiment as like shooting a cannonball at a piece of tissue paper or like Kleenex or Puffs, a cannonball. It should go right through. The fact that if you shot it at and some of them bounced back, you'd say, whoa, what's going on? Now, let me tell you something that's not in the book. When you're a graduate student, which I was, my advisor was Dr. Roosh, which I will forever be grateful for, did a great job being in his group. He taught me how to be an organic chemist. Think of yourself like a plumber's or electrical plumber's apprentice, and you're working with a plumber learning how to do plumbing. When you go to grad school, you're learning how to become a PhD chemist. And you work for an advisor, and he gives you a project to work on, and you do research for your PhD thesis. Now, when you get unexpected results and you go and tell your advisor, at least mine would, I'm sure Rutherford did the same thing. Grad student came in, I did that experiment, Dr. Rutherford, and some of the particles came back. What? Go do it again. And that's what happened to me when I got on it. Why don't you run it again 1 or 2 times? And you get the same results. And if it's really unusual and exciting, your instructor professor will come out and say, let's do it again. I'll watch you. And he sees it. I'm sure that happened with Rutherford. And because the particles got reflected back by the gold foil, where it should have gone straight through, Rutherford was able to come up with the following. What he found was, or proposed, 1, the nucleus, which is the center of the atom, which you should know. I think I have it on a later slide, but the nucleus of the atom is very dense. That's why it knocked back some of the particles, because the high energy particles hit the nucleus sometimes of the gold atom. And the other thing you should know, the nucleus contains protons and only neutrons. In the nucleus of the atom, the center of an atom contains protons and neutrons. I'll tell you later this chapter, where are the electrons? You'll just have to wait to find out where they went. But in the center of an atom, we have a nucleus, which is very dense, and Rutherford's gold foil experiments elucidated. Ooh, I used a fancy word. Elucidated means figured out that those have protons and neutrons. So you should know, nucleus of the atom, the center of the atom, contains protons and neutrons, and that's what Rutherford's gold foil experiments taught us. Now, when we talk about an atom, it has something called the atomic number. Oops, I have to be subtle again. One color. The larger I write, know this, the more important it is. And that's the atomic number. And what should you know? By definition, the atomic number of an element is the number of protons in a nucleus. And that means in that atom. The atomic number tells you how many protons are in that element. Now, what I don't have now, I'll talk about later. all of the elements, atoms, all the atoms of an element have a net zero charge. All the elements, atoms have a net zero charge. So if the atomic number equals the number of protons, which have a plus charge, and if all atoms of elements have a net zero charge, that also tells us the number of electrons. So once you know the atomic number, you know how many protons, how many electrons are in an element. Oh, where do we find this? I have a slide later on, but let's do it now. Here's our periodic table. In the upper right-hand corner, that's the atomic number. For hydrogen, H is 1. For carbon, C is 6. How many protons does hydrogen have? 1. How many electrons does hydrogen have? 1. The atomic number tells you how many protons and electrons. Let's look at carbon. How many electrons and protons does carbon have? Look at the atomic number. Carbon, you have to know or remember, start learning if you haven't, the chemical symbol and the name of the element and where they are in the periodic table. Carbon is C, has atomic number 6. And that means it has 6 electrons, 6 protons. You know something? I've been hogging all the fun. How many electrons and protons does oxygen have? Your turn. And don't forget to vote when you're done. Yes. All right, everybody's done. Oxygen, O, has atomic number 8, meaning it has 8 electrons, 8 protons. Let's go to another one of my favorite. Let's go to chlorine. How many electrons, how many protons does chlorine have? And looks like everybody's done, so it's my turn to have some fun. I say fun enough times, you might believe me. And chlorine, Cl, has atomic number 17, has 17 electrons, 17 protons. Oh, let's do one more. Let's go to the high rent district. How many electrons and protons does gold have? Got to know the chemical symbol for gold. I see someone's having the right answers, putting it in the chat. Thank you. Gold, chemical symbol you should know is Au. It's right here. It's got atomic number of 79, and that tells me it has 79 protons and 79 electrons. So on a test, I could ask that question, 1 point each. How many? Let's do one more. How many electrons? How many protons does mercury have? And everybody's done. Mercury chemical symbol, Hg, atomic number 80. That means it has 80 electrons, 80 protons. I just thought of something I haven't thought about, and I'm going to share with you. Let's see if I can even find it. Now, when I was a kid, they sold this toy like you see on the screen. They have from the 70s. We had even an easier puzzle. And in the center was a drop of mercury, and mercury is a heavy liquid at room temperature. And you go like this, and the back was, at least when I was a kid, was cardboard. Mine never ripped. What you don't know is mercury is a very hazardous substance. It's a poison. And what makes it even more hazardous, it's a cumulative poison. If you get enough poison, mercury in your system, it will eventually kill you. But even before that, it can do serious harm to your body. And they used to sell this toy with mercury in there, and it had a cardboard backing. And I'm sure a lot of kids ripped that backing, and now they were exposed to mercury. Small amount, but certain chemicals are dangerous. Mercury is one of them. All right, so the atomic number is the number of protons and the number of electrons in an element or atom of an element. Now, there's something called the atomic mass. I'm going to turn the switch, click off. I will never ask you what's the atomic mass number. Now, this is the sum of protons and neutrons in a nucleus. So the atomic mass number. Now, that's not the atomic mass you see in the periodic table. Really? Yep. Now, before I talk about that, I have to teach you, and I'll never ask on a test what it is, but this is an important concept you should know: isotopes. Isotopes are atoms of the same element that have different number of neutrons. And on our planet, in our universe, there's different abundance or amounts of different isotopes of certain atoms. And how many of you ever heard of carbon dating? It's used in archaeology. When you find old bones or wood or whatever, and what they're measuring is the amount of carbon-14, an isotope of carbon. Now, the main isotope of carbon in our life, like in your skin and everything, is carbon-12. And if I look at the clock, it's just about time for a break. So let's do this. Let's take a 5-minute break. I don't have to check my mail because there's no mail today. And I'll come back and continue. So I'm going to get up and stretch, and I'll see you in 5. Welcome back. No, all right, let's continue where we left off. Now, we were talking about isotopes, and isotopes are atoms that have the same element, have different number of neutrons. They have the same number of electrons and protons, but they have different number of neutrons. And because of that, different isotopes have different atomic mass number. I'll get to this in a little while, how this affects something you need to know in my class. Now, by the way, switch is totally off. Here's what's called a nuclear symbol. Now, in all the years I've ever worked in chemistry, I've never used this. So this will never be on my test, but at least somebody asked, did Dr. White talk about nuclear symbol? The answer is yes. And the atomic mass number is on top, and Z is the atomic number. Never used it. All right, now, there's a very important concept in chemistry called the atomic mass. And this is what's known as a weighted average mass of all the natural occurring isotopes of an element based on the abundance and mass of each element, isotope of that element. Now, some teachers have students learn how to calculate atomic mass based on the abundance. I don't, because in all the years of chemistry, I've never done it. You don't have to. But if we look at the periodic table, you'll see for carbon, it's 12.011. Sorry about it being a little messy. It's an old table. I don't know if I have a cleaner one. I'll have to look. I should take my scanner out. I'll see. But anyways, this periodic table, carbon has the number underneath is the atomic mass. Well, why is it that number, 12.011? Well, most of the isotope carbon 12 is the most abundant. And you multiply that percentage and you get a number. And then carbon 14 that has a atomic mass number of 14, and you multiply the percentage, which is very tiny, on our planet of that, you add two together and any other isotopes, and that's where you get that number, 12.011. If you look for oxygen, it's 15.999. And most of the oxygen isotope has a atomic mass number of 16, but there's a small amount of other oxygen. Same thing with hydrogen and the other elements too. And we'll won't use it now, but later in the semester, we'll use the atomic mass, the number underneath the element. Now, let's have a little fun. We've done some of this, determining the atomic number, the number of electrons and protons, and the atomic mass of an element. So let's go to our friendly neighborhood periodic table, and let's look at how many electrons and protons does, and what's the atomic mass of sodium. And I'll do this one, then I'll let you have some fun too. If we look here, sodium, you should know, has a chemical symbol Na. The atomic number is 11, excuse me. And that tells you it has 11 protons and 11 electrons. And the atomic mass, the number underneath, is 22.989. And like I said, later in the semester, I'll teach you a lot more about that number and how you can use it. All right, let's do another one. I'll let you try this one. How many electrons and protons, and what's the atomic mass of sulfur? And everybody's done. My turn. And sulfur has the chemical symbol S, atomic number 16, and therefore it has 16 electrons, 16 protons, and the atomic mass is 32.066, the number underneath. Oh, let's do one more. These are fun. Let's do copper. How many electrons, how many protons, and what's the atomic mass of copper? Your turn. All right. Copper has a chemical symbol Cu, and it's right here. And it's got an atomic number 29, which means it has 29 electrons, 29 protons, and the atomic mass is 63.546. And this is a skill you should have. Now, earlier I talked about the nucleus of an atom, of any element, is the center, and the center of the atom, the nucleus, contains the protons and neutrons. Where are the electrons? Well, that's called the electronic structure. And in order to explain where are the electrons, I have to do some background information for you. And for next couple of slides, click, will this be on a test? The switch is in the off position. All right, now in our world, we have what's called electromagnetic radiation. And this is energy that travels as waves through space. And a wave has a wavelength, how long is the distance between the top of the waves, and a frequency, how quickly are they coming in. Like if you were to go and watch the waves of the ocean, Lake Michigan isn't that impressive unless it's a storm. But if you go to the East Coast or West Coast and look at, say, the West Coast of the Pacific Ocean, and I've been there and I've done that, it's fun. I've gone on business to California a lot of times, and the waves are coming in, and electromagnetic radiation is just like that. Now, we have what's called the electromagnetic spectrum, and this is the arrangement of all energy in decreasing order. And let me find a nice one on the internet to show you. Let's try that again. If you look on your screen, they have here electromagnetic. Whoops, let me get back to that again. Electromagnetic spectrum. If you notice, you have gamma rays, X-rays, ultraviolet, infrared, visible in the center, microwave, and radio. Now, all the way on the left, gamma rays are the highest energy. And as you go toward the right, you have lower energy. And in the center, you have visible light, and visible light is made up of different colors. And each one has a different energy. You put them all together, you get the white light or the sunlight we have in our world. And here's another way of seeing it. Again, gamma are the most powerful. X-ray, UV light is more powerful than visible, which is why it can damage your skin if you're out in the sun, because there's also UV light in the sunlight. So each of these electromagnetic energy of the spectrum has a different wavelength and frequency. And you see that underneath here. Now, it turns out there's something called atomic spectra. Again, click, switches off, but this is important background information. And the atomic spectra, when light emitted from a heated element is passed through a prism, prism will separate the light into different bands. And if you know about Pink Floyd, they use this on their, I forgot what album it was, but, or is that their, hold on. And it's on one of their albums is Prism. And if you notice, when light goes through white light, it separates into different colors. By the way, when I was young, my father was very nice to me, always was, and he got me this nice prism. We got it at the Museum of Science and Industry. It had a little chip in it, so it was reduced, but it's huge, and I still have it. I still like holding it up to the sunlight doing that. Now, you know I'm a scientist. But anyways, if you have, instead of white light, the light that comes from heating an element, some of these bands like violet or whatever will be present. And if you see on your screen right here, here's an example of doing an atomic spectrum of hydrogen. You heat it up, put electrical charge through it, light comes out, put it through the prism, and you see these three lines. Let's see if I can get it bigger. And it's not super bright, but you see 1, 2, 3, actually 4 lines of hydrogen spectrum. Now, if you look at iron, you've got a lot of lines. Helium, you can't really see, but it's just got a few. And here's the whole visible spectrum. Well, what does this mean? These different lines are associated with what's called, again, switches off, electronic energy levels. Association of lines in atomic spectra with changes in the energy of electrons. Now, these energy levels are assigned values called principal quantum numbers, N, and these energy levels are also called shells. And this is where we get into where are the electrons? Uh-oh, I better get subtle again. And know this, where are the electrons? The electrons are in the electron shells of an element. All atoms are made up of electron shells. And I won't ask you what the definition of them are, but you should be familiar with it. Know this. Now, an electron shell is the region of space about the nucleus that contains electrons that have approximately the same energy and spend most of their time approximately the same distance from the nucleus. And remember, the nucleus is the center of an atom. So all around the nucleus, we have these shells that are a certain distance from the nucleus. And that's where you'll find electrons that have the same energy. Now, each electron shell has electron subshells. And you should know that, be familiar with, I'll never ask on test what's an electron shell or subshell, but I will use that terminology. An electron subshell is the region of space within an electron shell that contains electrons that have the same energy and they're also the same distance. Notice an electron shell, they're approximately the electrons, same distance and same energy, approximately. But in the subshell, they are the same energy, the electrons in a subshell of a shell, and they are the same distance, I didn't write that down, from the nucleus. So we have electron shells, and each shell, it has subshells. Now, the electron shells have very fancy names. There's shell 1, shell 2, shell 3, and shell 4. Now, how many subshells in each shell? Well, this is real difficult. Shell 1 has 1 subshell. Shell 2 has 2 subshells. Shell 3 has 3 subshells, and shell 4 has 4 subshells. Now, I've mentioned, and maybe not enough times, but I'll mention it now. A couple of years ago, one of the faculty member at COD, who I know and teaches chemistry like I do, challenged me. He says, on your test, because I found out he gives important information to help the students out during a test. And he asked me, are your tests supposed to test how well a student understands chemistry, or are they supposed to test how well a student understands chemistry and how good their memory is? And I said, I'd like the student chemistry. Well, he says that that's why I put important information, because I'm not testing their memory. I thought, that's a good idea. So a while ago, about almost 3 years now, I've been doing this. And let me get to open up something for you. I can find it. I've lost, there it is. Now, on the back of test number 1, I will have this page, and there are different ones for different tests. And this is stuff you don't have to memorize. In the past, when I taught this, students had to memorize things like this. And notice I have a table with the electron shell. You have to know how to interpret this table, but you don't have to memorize it because you'll be given that. And as I pointed out, shell 1 has 1 subshell. Shell 2 has 2 subshells. Shell 3, 3 subshells. And shell 4, 4 subshells. Now, I haven't cut out memorization totally. And one thing I don't have on here, but I'll put it on. Let's try a straighter arrow. That's better. Shell 1 is the lowest energy electrons. And as you go down the table, the electrons have higher energy. The highest energy on that table is shell 4. And this is something you need to know. So we have a shell where the electrons are approximately the same energy and same distance from the nucleus. Notice I do nucleus, the center of the atom. And shell 1 has 1 subshell, and shell 2 has 2, and 3 has 3, and 4 has 4. Now, let's talk about the subshells. Now, the subshells were given letter designations, S, P, D, and F. And S is the lowest, by the way. You should know this. Now, the subshell designations are S, P, D, and F. And S is the lowest, and F is the highest energy subshell. Another way of putting it is this: for energy, now this symbol means less than. So S has a energy less than P, P is less than D, and D is less than F. Now, I will not ask on a test, but a while ago, a student asked me, what does S, P, D, and F stand for? And I'd forgotten, so I looked it up, because if I don't know a question, answer, I'm not going to lie about it. I'll say I forgot. And I looked it up, and from the original atomic spectra, someone came up with the idea that the S subshell had a sharp line. They called the line on the spectra for P subshell principal, D is diffuse, and F is fundamental. How they came up with that, I don't know. That's not my area of chemistry. I'm an organic chemist. we don't do atomic spectra. Now, when it comes to electrons in the subshell, subshell S, you can only put 2 electrons. Subshell P, you can put 6 electrons. Subshell D, maximum number of electrons up to 10, and F up to 14. So we have these shells and subshells, and those are where the electrons are. Now I'm going to turn the switch off, click. There's also something called orbitals. That's a region in the atom where the highest probability of finding electrons are. Orbitals of different subshells have different shapes. Again, switches off. S is circular, like a globe. If I could stop time, if I were that powerful, and by doing that, all movement has stopped, including the electrons, which are moving around an atom, not like the planets around the sun. It's different. Most people think of it that way, but that's wrong. If I could stop all time and movement, if I had an electron in an s orbital, it'd be in a sphere a certain distance. That's where I'd find it. Now, if we're in a p orbital, it would look like an hourglass. And it could be here, 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 or here, or here, but it would be in this general area. And that's where the electron would be zooming around. I don't know if they zoom, but they move. Now, electron subshells are filled in order of increasing energy. Now, that I'll talk about in a little while. Electron occupy orbitals of subshells such that each orbital acquires 1 electron before any other orbital acquires a second. And since I'm not going to talk about orbitals in this class, you can ignore that. And you can have no more to same thing as this one, 2 electrons in an orbital. So what does this all mean? Where are the electrons? Well, we show where the electrons are by electron configuration. Now, an electron configuration is a statement of how many electrons an atom has in each of its subshells. And hint, number and letters only. See board, for example. Before I do that, now when we talk about a subshell, you just don't say S. A subshell is made up or named with a number and a letter. A subshell of an atom where the electrons are, the name of that subshell is always a number and a letter. Important. You should know this. A subshell is made up of a number and a letter. So what do? How do we do this? Well, see board, so I better get to work. All right, let's take a look at this. It says about 4 or 5 points, depending on my mood when I'm writing a test. Draw the electron configuration for, and there may be an A, B, and C. Lithium is A. Well, how do you do that? Well, in order to do the electron configuration, the first thing you have to find out is how many electrons. Now, lithium, and you don't have to write this down, but I will, has the chemical symbol La, Li. When I say Li. If we look here, lithium, how many electrons? Because we're talking about the electron configuration. We're trying to find, first of all, how many electrons are in that atom of that element. And the answer is 3. So we have, and you don't have to do this, but I like to write things down. I have 3 electrons I have to deal with. So what's the first shell of an atom? Well, if you look at this table, it's shell 1. And let me go to the other one. It's shell 1. Mother Nature always fills the lowest energy shells first and then goes down the table. So shell 1 is the first subshell and it has 1 subshell. Now I didn't write on this here and I should have. Now, shell 1 has 1 subshell. And remember, a subshell is a letter and a number. And the subshell is S, but it's really 1s. And 1s, I can put in 2 electrons. So I'm going to do that. So I have my first shell has 1 subshell, 1s. The maximum number of electrons I can put in any s orbital is 2. So I show that by a superscript 2 to the right of that letter. Remember, a subshell is a number and a letter. Well, I have 3 electrons. I've done 2. I have 1 more left because 3 minus 2 equals 1. Well, what do? I filled up shell 1. It only has 1 subshell, which you can put in 2 electrons. Now I have to go to the next shell. And that's shell 2. Now, shell 2 has 2 subshells. And what's the first subshell? You start here, the lowest energy, 2s. And 2s, like 1s, you can put a maximum of 2 electrons. But I only need 1. And this is the electron configuration of lithium. 1s2, 2s1. Remember, a subshell is a number and a letter, which you see there. And the electron configuration tells me where the electrons are in the subshells of each shell for that element. All right, let's do another one. Ooh, let's do my favorite. Let's do carbon. Well, the first thing you have to do if you're going to draw the electron configuration for carbon, 4 or 5 points each, is find out how many electrons does carbon have. And how do you do that? You know the chemical symbol for carbon, and hopefully you've learned them by now, the 37 I asked you to learn, is C. And what's the atomic number of carbon? 6. And the atomic number tells you how many protons and electrons. We're interested in the electrons, and that is 6 electrons. So we have 6 electrons. What's the first shell? Again, you start at the lowest energy, and that's shell 1. And it has 1 subshell. And that is, the lowest energy is S, 1s. And that 1s subshell, you can only put 2 electrons. So for carbon, I have 1s and I can put in 2 electrons. Well, it's got 6 electrons. I have 4 more to go. Shell 1 has 1 subshell, as you can put 2 electrons in. I filled it up. So I now have to go to the next shell. And that's shell 2. And shell 2 has 2 subshells. What are those? Well, let's go down. The lowest energy would be S, but you need a number and a letter, 2s, and P, 2p. Now, S, I can put a maximum of 2 electrons. Ooh, 6. I can put a maximum of 6 in 2p. So you need to look at this chart. In the past, I had students have to memorize this, but now you just have to look at the chart and know that S subshell, meaning 2s, remember subshell is the number and a letter, we're in shell 2, subshell S, 2s, I can put in 2 electrons, and in 2p, I can put in 6. So let's see what that means. Well, I filled up the first shell, and this has 2s. How many electrons can I put in there? 2. Now, this is 2 plus 2, 6 minus 4, 2 plus 2. I have 2 more electrons to go, and 2 has 2 subshells, 2s and 2p. Now, I can put a maximum of 6 electrons in 2p, but I only need to put 2 in there. So now I'm done, and that would be 1s2, 2s2, 2p2 would be the electron configuration for carbon. Now, one of the things I should point out, when you get to the very higher atomic weight elements, some of these rules have exceptions, a lot of them. And you could spend the next 2 weeks learning all those exceptions. and maybe do good on a test, maybe not. It's time for a special gift from me, Dr. White. After I get some water, and that is, don't tell anybody I'm being nice and give me a special gift. For my class, I'm only going to ask you to learn how to do electron configurations up to magnesium. For my class, I'm only going to ask you to learn how to do electron configurations up to magnesium. And that's going to make your life a lot easier. There are other things I'd rather spend more time on than learning electron configurations. It's important, but there are more important things, and you'll see later on this semester that I'll have more time to talk about those things. But again, you only have to know how to do electron configuration up to magnesium atomic number 12. Ooh, let's do one more of these. Another nice element I like, sodium. And that's the chemical symbol Na, which you should know. Well, if we're going to do the electron, have to draw the electron configuration for sodium, we need to know how many electrons sodium has. And where do you get that? From your friendly neighborhood periodic table. Sodium, chemical symbol Na, and you should know these symbols, has atomic number of 11. So if we look here, we have sodium, and I like to write down 11 electrons. You don't have to put the minus sign on top. I have it. I don't know where I picked that up. So where do we start? This table will be an important information. Test number 1, as I showed you. The first shell always that you fill electrons, shell 1, and it has one subshell. And that subshell, remember you start with the lowest energy subshells, is 1s. Remember, a subshell name is a number and a letter, not just a letter. And how many electrons can I put in 1s? 2. So I'm going to do that. Well, I've got 2 done. I've got 9 more to go. Now, shell 1 has one subshell, 1s, and you can only put 2 electrons in there. And once you've done that, it's full. And you have to go to the next shell, next lowest energy shell. And if we filled up shell 1, we now go down the next energy, and that's shell 2. And shell 2 has 2 subshells. And what are they? And this table will be given to you also. You start from lowest to S, which you can put 2 electrons in, and 2p, you can put up to 6 electrons. So let's get back to our work. We go to the first next shell 2, and the first subshell is always 2s, and any s subshell, I can put 2 electrons. Now, shell 2 has 2 subshells, 2s and 2p. How many electrons maximum can I put in 2p? In case you forgot, 6. So I have 2 plus 2 is 4. I got 7 more to go, so I can put 6 in there. If you add these up, 2 plus 2 plus 6, that's 10 electrons. But I want to have 11 electrons. I have 1 more electron to go. Now, in shell 2, you have two subshells, 2s and 2p. 2s, you can only put 2 electrons, 2p, or any p orbital, 6 electrons. Well, guess what? I filled up shell 2. What do I do? Because I have one more electron to go. Well, I filled up shell 1, shell 2. Now I go to shell 3, which has 3 subshells. Well, what's the lowest energy subshell of 3? Shell 3, 3s, which I can put maximum of 2 electrons. So since I filled up shell 2, I now go to shell 3. The first subshell is 3s. Remember, a subshell is a number and a letter. And I have 1 electron to go. I can put 2 in there, but I only have 1, and I'm done. And the electron configuration for sodium is 1s2, 2s2, 2p6, 3s1. And that's how you do it. Now, let me remind you, don't tell anybody, shh, it's a secret. My gift to you this semester is you only have to know how to do electron configuration up to 12 magnesium. And that should make your life a lot easier. Shh, don't tell anybody, I'm being nice. And that's how you do it. If I look at the clock, let's see what's next on our list. This would be a good time to say I'm done for today. We did a lot. I apologize for not remembering today was a no school, no class holiday. But since I'm putting this on video, if you didn't come, I would have still given a lecture if nobody showed up and put it on video. I've done that once or twice when people that nobody showed up. I still do a lecture. But anyways, couple things. Don't forget, do the practice problems. They will help you with my test. Don't forget, there's a lab due tomorrow. Hand in labs. They help you. Don't forget to put a selfie like we did. I think the last one was with the Alka-Seltzer, that or your balance or something. And if you have any problems, even though I don't have to, but I'll do it anyways tonight, you can come to my office hour, or Wednesday night, come to my office hour for help. And with that, I'll say, gehen gesund. Remember, that's Yiddish for go in hell. This pandemic is still running, but not like it used to, thank God. And with that, I'll say, gehen gesund. Goodbye. See you tomorrow.